Alright. So my announcement is about labs. If you didn't already know, I'm the one that grades those. So lab 1 grades should be out. I think I put them up last night. Most of those things went really smoothly. If you feel like there's some type of error, you're not sure about any of my comments that I put down there, please send me an email. Just put in the subject like 2048 lab 1. Good enough, right? I'll know who you are. I'll be able to find it and make things work. Lab 2 grades will be up by like tonight or tomorrow. You just need to look through them one more time. This one was harder because WebCourses decided that it didn't want your group numbers to be normal. So please, for these ones, like actually read through my comments. If you have questions about anywhere that you lost points, again, feel free to reach out to me over email or like meet me at the end of class. And then if you realize that I accidentally somehow put a different grade for you and your lab partner, also reach out to me. That should not be the case. That means I need to go back, double check, and make sure that that grade is the same for everyone in one group. Questions about that? Okay. So yeah, any confusions, feel free to reach out.
All right. Cool. So today, and I forgot to download this. So hopefully it should all work well. I'm using a different laptop today, but that should hopefully be better, not a bad thing. So today we basically finished Newton's laws last class. And just to show you all the calendar, since I finally do have this open, here's today, here's the test. It's 2 weeks. It's nice to have a nice visual showing that it's, looming. As I mentioned, you all, my office hours. So interesting enough, so if you ever want to come to my office hours, you don't want to be super crowded. I think Monday and Wednesday are the best days. So Monday I had like 2 people. Then Tuesday I had 11. And then yesterday I had 4, I think. And it makes sense, on class days, more people are going to come, which is awesome. I want you all to come. But if you're like, man, I'm really worried about it being super crowded in there. Monday, Wednesday seem to be the day. Another thing I'm thinking of doing, I've not committed to this because there's stuff I have to figure out. Something else I'm thinking of doing is on the week either of the test, instead of having my office hours in my room, maybe trying to find, maybe this room's available at some times. I fully expect to have way more people on test week because that's how that stuff goes. And so I have to look into this, is if there's a room I can rent out, like this one or something else, and use that instead. So that way I can have a bajillion people in the room. But that is me telling you I'm going to look into it. And, if that ends up being the case, I will inform you all through an announcement and through class and all that good stuff. But I can't commit to it because I just haven't looked into it yet. So, that's how those things go. All right. So there's all that. So I realize I have to download the other one. As always, y'all can see all my organization. All right. So let's kind of quickly scroll through and remind you all of Newton's laws. So circular motion we talked about, it was really straightforward. I'm actually going to kind of just jump through the slides of interest. Remember we talked about arc length. So that was S, which is a weird variable for it, but it is what it is. S is kind of how long that arc is, and it's just r theta. And then we talked about tangential velocity, and we had Leo toss something. It wasn't my duck, but it did the job. And that says that if you release something, it goes in a straight line, and that's the path it's going to go. It's the velocity at any point, tangential to the circle, 2 pi r over t. Woohoo. And then we talked about centripetal acceleration, which is vt squared over r, which says that in the picture here, that was the moon, that's the Earth orbiting the sun. And the whole point of this was that acceleration is towards the center, which is important. Anything going in a circle is accelerating, even if the number for its velocity is staying the same. So that was the big takeaway there, that things that change direction are accelerating. Things that change direction are accelerating. And then we got into Newton's laws, and we looked at him and said, wow, what a guy. Let's just take him in for a second. What a guy. Absolute mad lad, absolute genius. One of those people that just stands out. There's people that make history, and he is one of those people. Hence, we talk about them now. So we talked about Newton's law. So we went through the 3 laws. So we had Newton's first law, which says an object in motion remains in no motion, object rest remains at rest. One example I didn't give for you all about this that I should do in the future. This explains why you wear a seatbelt, which is it's going to make sense once you know about it. So I need a whiteboard. So this is really easy to show why you need a seatbelt. Obviously you all probably know this at this point, but why does this relate to Newton's first law? All right, so I've mentioned this in the past. We've had some problems with this. If you're in a car and the car is going 60 miles per hour, you are going 60 miles per hour. That is the case. If you're not going 60 miles per hour, then you're not moving. But you're in the car, so you're moving. Anyway, so here's you in the car, and here is the car. And you're trucking along, and if you hit something abruptly, you don't know to stop. There is nothing in your body that says, oh, the car stopped, I better stop with it. Like that, no. You are going 60 miles per hour, according to Newton's laws, until something stops you. And you get to make the decision on what's going to stop you. Is it going to be your seatbelt, which will, have a bit of time on it and it's not hard, it's got some elasticity to it? Or is it going to be your steering wheel? Or your windshield? Or a wall? If you fly through the windshield and then hit the wall. So, something will stop you when you hit something. You get to decide what that something is. The airbag also exists, but if your car goes sideways, if you don't have side airbags, you're going out the window. The most dangerous thing that can happen in an accident is you leaving the vehicle, because outside the vehicle are all sorts of hard objects, like walls and floors and other cars. That's why motorcycles are so dangerous. If you hit something in a motorcycle, you are leaving the vehicle. That is basically almost a guarantee. You are going to hit the wall, floor, stuff like that. But this is Newton's first law. Newton's first law also explains why when you make a turn and you feel yourself getting kind of pulled to the side, nothing is pulling you. You are just wanting to keep going in the same direction. Look at that. My whiteboard turned and my eraser kept going in the same direction. Newton's first law also explains why you get pulled outward on turns. Nothing's pulling you. You just want to keep going the same way and your car's going a different direction. So the seatbelt's got to pull you. Otherwise, you're not going to make that turn. And you probably want to make that turn. You probably want to stay in the car. So it's crazy how many things Newton's laws explains. Far more than you may realize. But that was one that I forgot to mention that is very worthwhile. Because everyone experiences that. You take a turn, you get pulled to the side, and everyone, you probably haven't thought about it too much, but it feels like you're getting pulled. You are not getting pulled. Well, okay, technically you are. You're getting pulled in the direction the car's turning. But nothing is flinging you to the outside of that curve. It's actually quite the opposite. Something is pulling you to keep you in the curve. You're accelerating. Wow, centripetal acceleration. All right, Newton's second law, F equals ma. And this is where I started to stress. There's a couple things here. Remember, a big thing in space is hard to move. That was the example. So funny enough, I did this in my lecture class. So with you all, I was able to talk more, and you were able to talk to each other. And the vast majority of you all got this problem right. This one here about not that one. Nope, we'll get there. Where is it? The one it's the one before this. The truck. There it is. Wow, we got there. All right. What's harder to speed up in space? Something small or something big? So this again just shows the benefit of working with other people. This is not a knock on my lecture class. My students in my lecture class have the same. They're no different students than you all. So if we take like average intelligence, they're going to be exactly the same as you all. But what's different is you all are able to talk to each other and actually have time to think in the class and things like that. I think 80% of my students got this wrong in the lecture class, whereas like the opposite occurred in this class. Not because you all are smarter, but because you're able to talk to the people around you, you're able to spend more time thinking about it. This is just me continuing to remind you all working with other people is important. There's a reason we do this. There's a reason why this class exists. There's a reason why I continue to push you all, even outside this class, to do so. But yeah, things with mass. Mass is what matters, not gravity. And then we got to the car one, and everyone hates this one. This is the whole fly hitting so getting into Newton's third law. fly hits a truck, which experiences a greater force. The force is the same. The force is the same. But the fly will accelerate a lot more. And we did the math. It will accelerate 2 million times more. And therefore it dies. And the punchline here, it's not about force. It's about acceleration. If I told you I pushed something with 1,000,000 newtons, you actually cannot predict what's going to happen. I haven't given you enough information. I pushed something with 1,000,000 newtons. What's going to happen? What am I pushing? If I push the Earth with 1,000,000 newtons, nothing's going to happen. The Earth's got a lot of mass. If I push this little box with 1,000,000 newtons, it's gone. It's absolutely out of here because it's got a little bit of mass. Newtons doesn't tell you what's going to happen. Acceleration does. If I tell you something's accelerating with 1,000 G's, I don't care what it is. It's booking it. Like, you don't need to know any more other than that thing's going to go really fast. If I tell you acceleration, that is sufficient for you to be able to tell what the object's going to do. If something has an acceleration of 5 meters per second squared, it doesn't matter what the object is. You can imagine what's going to happen to it. Whereas when it comes to force, you have to have mass to be able to then take it to acceleration and draw meaning. All right, and then we got to the end, and we learned about free body diagrams, and I told you all they're vectors. We have to draw a picture. We get to add vectors, and that is literally what we're going to do now today and this next week. Is basically I'm going to give you a bunch of different forces, and you're going to learn how to identify them. You're going to learn how to draw free body diagrams, and just basically do this. You're just going to be doing this for the next week and a half. The key will be just learning different forces. We're going to learn about friction, gravity, spring force. That's our lab today is on spring force. Applied force, which is literally just any push or pull. So it's going to be a good time. So let's jump over to that. That's not it. It's very sad. That's it. All right. So we're going to jump into application of Newton's laws. So we actually finished that entire PowerPoint last time. I did not expect us to get through this. We'll get through some subset of this. I'm not too picky. So we'll probably go through this for maybe 45 or 50 minutes. Then we'll be where we're at. And then we'll start doing the lab today. So something that's going to be a little different with the lab today is, in the beginning, I'm actually going to spend some time having you all try to come up with the experimental design. I have kind of a general experimental design that we are going to follow, but I'm going to basically see if you all can figure out what it is. I'm going to have a goal, and then you're going to see, can I come up with an experiment that would measure that? Because the reality is, when you're working in a job, sometimes you will have a set procedure, do this, then this, then this to test something, but you start getting paid the big bucks when you're the one coming up with the experiment. Where they say, I want to figure this out, and you come up with the experiment. That's much harder, way harder. Following a recipe is really easy. Coming up with your own recipe, if anyone's baked before, it's way harder. So anywho, to that end, we're going to talk about different types of forces. I have a big old list. We're going to go through them. Then we're going to draw some free body diagrams. It's going to be a good time. Okay, so, these are basically what you need to know to be successful in this. You need to be able to draw free body diagrams. And to that end, adding vectors and adding vectors X and Y are separate. That is going to be, we are going to work with vectors. So kinematics has vectors. Forces has vectors. Energy doesn't. So when we get to energy, you're spared for a short period of time. So energy won't be on the next test, but it'll be after that. And then when we get to angular motion, we're going to be back to torque, that kind of stuff. But it's really important. Sometimes you have to work with them, sometimes you don't. All right, great. Here's all the forces we're going to work with. Gravitational force, normal force, tension, spring force, friction, drag, and centripetal, which I think I say separate slideshow, but I think it is actually this one. Okay, I mentioned the word drag here, and I've told you all this. We are going to calculate air resistance, but this is a big but, which is a fun thing to say. Here's how we're going to calculate air resistance. So air resistance, just to kind of give you all a heads up what this is going to look like, it's going to be applied force is 100 newtons. Force due to air is question mark. Net force is 80 newtons. Find the force due to air resistance, okay? So 100 newtons to the right, blank to the left. If you add those, so basically this problem ends up becoming 100 equal, 80 net force. Let's write the whole thing. I'm mentioning this now because this is an important distinction. So F net equals FA plus negative F air. The force due to air is to the left, force applied is to the right. You plug in the numbers and you get the force due to air resistance is 20. Okay, so we're going to calculate it, but we are not going to calculate it. There is an equation for the force due to air resistance, and I'll mention it when we get to it. We will never use that equation on any problem in this class because it is a nightmare. There's forces involved. If something's accelerating, its velocity is changing. The force due to air resistance depends upon velocity squared. So that means as something is accelerating, the force due to air resistance is constantly changing. So you actually have to do integrals and stuff like that. And it's incredible. Air resistance is incredibly complicated. Air resistance is incredibly complicated, which is why we will never calculate it in this class, in the full and detail way. That's why we always say assume no air resistance and all that stuff. Air resistance is not trivial at all. It's, oh my gosh. There's so many variables, but we'll get to that, and I'll mention it a bunch of times because it's interesting. All right, cool. All right, let's see how you all are free body diagrams. We talked about them last time. Following is the correct free body diagram for you sitting in your chair right now. You are a box. Remember, that is the starting place. Any object you have, you just draw as a circle or a box. If you want to, you could actually draw what it is, but that takes time. So it doesn't have to be a box. That's just kind of traditionally what we do because it's easy. So which of these is you? Is there only a force pulling you down? Is there a force pulling you down and pushing you up? Is there no forces acting on you, or is there not enough information? These pictures show you all the forces acting on you. I didn't label them purposely. All right, we'll leave that going.
I have a question. So
All right, what say you all? Perfect. Alright. Cool. Alright, I'll give you all 10 more seconds. We're looking pretty good. I think. Oh. Just having you know. Alright, 3, 2, 1. Alright. Bada bing, bada boom. Alright, so I went around. Some of you know I've confirmed that you have the right answer. Who wants to express what? Who wants to convey the info? Yes.
So it's B.
It is B. How come?
Because there's the gravity pushing you down, and there's the normal force from the chair.
There we go. So we have gravity. So when you draw these pictures, you will actually label them. That is important. I didn't label them on purpose because it kind of gives away a bit too much for this. So you have gravity, and then we do call this the normal force. Now, if you're like, but I haven't learned normal force, how was I supposed to know that? That's a good point. And I didn't need you to know the name of it. So all I need you to think about was, are you accelerating right now? Are any of you all speeding up or slowing down? No. Your net force is 0. So this is something we're going to do in this class. Remember, F net equals ma. Therefore, and F net also equals, in this case, Fn plus negative Fg. I am not accelerating. You are not accelerating. None of you are speeding up or slowing down. So all the forces are canceling. Yes, gravity is pulling you down. I think everyone's on board with gravity pulling you down. The question is, why aren't you falling then? Because the chair pushes you back up. Stuff that sound like, this is fairly obvious when you think about it. Yes, obviously you're not falling. But so I am trying to take the things that are obvious to you. Yes, gravity's pulling you down. Yes, you're not falling. And we have to learn how to express that in the picture. That's what I'm teaching you all here. I'm teaching you how to take something that's kind of obvious and you know, and how to express it in a picture and then be able to do math with it. All right. Now, my phone's been yelling at me because it's our favorite time. UCF here time. Leo's here for you if your phone hates you. Well, it's not your phone. It could be your phone. Who knows? And you know what? With the advent of AI, maybe it is possible that one day your phone will hate you. Who knows? We say it, can a phone hate? There it is.
I think because it's so blurry, that's why it stops.
No problem. Any screen works.
Okay.
Yeah, feel free to use my laptop if you want. There it is. All right. So if it's not working for you, just, call over Leo. It's a good chance to get to know him. Ask how he's doing. And he will find you. It's not ideal, but the system works. So, opposite corners, good. He's going to get his steps in today. All right, moving onwards. So we're gonna we're gonna break this into pieces. We're not gonna do all the forces in one go. So we're gonna start with the gravitational force, the normal force, and I guess tension gets lumped in here as well. Gravitational force and normal force are tied together. We're gonna see that. Actually, you already did see that. On the last picture, they were equal to each other because you're not moving. So, the normal force is always connected. Well, okay, it's not always. The normal force is often connected with gravity, but not always. There is a problem on the clicker set the problem set that's that way. All right, gravity. It's exactly what you'd expect. You could probably derive this expression yourself. F net equals mg. F net equals mg. You're close enough. All right, F net equals mg, really straightforward. How do I derive this? Oh, man. Well, remember F equals ma? What's the value for A when it comes to gravity? Oh, it's g. Okay, something that's really important to point out here. Something that's really important to point out here. I recommend you, when you plug numbers in here, I recommend that you put G as positive 9.8. I recommend you all put G as positive 9.8. You can put negative and it's fine. You can put negative and it's fine. But the reason I recommend that you all put G as positive 9.8 is I don't want you to double count the negative. I don't want you to double count the negative. So let's just take a really easy problem. Let's say I have something falling. And let's say it's getting pushed upwards with 2 newtons. And then it's experiencing a force of it has a mass of, again, 1 kilogram. Nice and easy. So if I want to find the force due to gravity, it's going to be m times g. And so the way I do these, I put g as positive. So I do 1 times positive 9.8, and we get the force of gravity is 9.8 newtons. We're always going to find net force. Like, that's always going to be the case in these problems. So we're going to add these forces together. And at this point, so I'll do 2, and then I'll do plus negative 9.8 newtons. I decide the negative when I'm setting up the net force equation. I decide the negative then. If you put G as negative 9.8, and then in the net force equation, you then put another negative, you're going to cancel out your negatives. Okay, so let me kind of give you that case. Let's call this FA. So if I have FA plus negative FG, because I'm like, oh, FG is downwards, I'm going to make it negative. That makes sense. If you decided to make FG negative here, then you would do 2 plus negative 9.8, and that's wrong. Do not double count the negative. Do not double count the negative. Okay? So that's where I just recommend anytime you all calculate these forces, calculate them as positive numbers. And when you set up the net force, when you're adding up all the things, then decide positives and negatives. Say to the right is positive, left is negative, up is positive, down is negative. Don't decide negatives twice. Otherwise, you cancel yourself out and you make a mistake. Okay? So, anywho, that's a recommendation. You'll see it when you practice it. You might learn the hard way, like accidentally make a mistake on it. That's fine. That's good. Any of these things I mentioned, if you end up making a mistake on it later, that's fine. I don't really care as long as that mistake happens before the test. All right. Make me proud. If you have a mass of about 70 kilograms, what is the magnitude of the gravitational force acting on you? And the word magnitude means absolute value. Magnitude means absolute value. That's why none of these answers are negative. Magnitude means absolute value. Very nice, very nice. All right, give you all like 20 more seconds. What do y'all think about here? Which one? Okay, I'll go. Why wasn't it 16 kilograms? Good, good. All right, we'll close this out in 5, 4, 3, 2, and 1. Boop. All right, who's confident? Should be something like lots of y'all should be. You look confident. You looked at me.
D.
Why D?
Because the F equals ma, the mass is 70, and A is
There you go. And so there's two answers here. It is, if we go through all the rigorous steps, M equals 70 kilograms. The problem-solving process continues to be useful even in these problems. I just want to remind you all that, yes, you're not maybe always going to want to write out all this. You don't always have to write out all this. But I do want to remind you this is the thought process you did whether you realized it or not. And the more you write out, the less likely you are to make a mistake. We are solving for FG. The equation for FG is M times G. And yeah, easy peasy. FG equals 70 times 9.8. Can we put that positive in there? Because it says magnitude, and that's positive. So it's 686, and there's two answers. It is the Newton's one because units matter. If you do not put the right unit, it is the wrong answer. 686 newtons is not the same thing as 686 kilograms. They are. It's apples and oranges. You have to use the right unit. It sounds silly, but if you don't put the right unit, someone that reads it later on will not know what you're talking about. If you told something the answer is 686 kilograms, you just told them it's mass. And that's a completely different thing than force. So very, very subtle, but very, very important. If you don't speak the language correctly, people won't understand you. Math is a language. All right. Did we already do this one? I think we did this one already. See if y'all can do it real quick. See if you remember how.
Oh, we did.
Yeah. See if y'all remember how to do it. I know we already did it, but it's just as if you already did it, it'll be easy. Don't look for your previous solution. Do not look for your previous solution because that defeats the point. That says that past you knows it. I want to know if present you knows it. Present you isn't past you. Time has passed. You've changed. Cells in your body have died. Other cells have replaced them. So do it fresh. If you look at your previous solution, you're cheating yourself on learning. Draw a picture first. This is on Earth. Oh, and the answer is not 12.5. The answer is not 12.5 meters per second squared. This thing's on Earth. You got to draw a picture. A force problem, every force problem, draw a picture and draw all forces acting on it. If it doesn't say there's air resistance, assume no air resistance. Every one of these force problems, you start by drawing a picture and labeling all forces acting on it. Then you will add them all up. X's together, Y's together, and then you set it equal to NA and you do math. That's going to be the recipe we're going to do again and again and again and again and again. Oh, yeah.
Right, that's right.
No picture. Picture will help. Picture will help. Picture. That's what we do. Try to picture in your mind.
Yeah.
That's one of the forces. So that's mass. And then after that, what does it say? Gravity. Arrow going up. Yeah, and I'll have this in a nice Okay. It's getting pushed up. It's a constant. So this is a rocket. Let's just say it's a rocket. Yeah, it's a constantly. Yeah, so anytime I mention these, it's an ongoing force. Because if it was just a single push, so we find the acceleration at the instant it's getting pushed, which is, so that's the part we care about. But then the cool thing, and I need to include one of these problems. Once you find this acceleration, you can actually do kinematics problems with it now, stuff like that. But I haven't included enough of those problems, to be honest. All right, so just to give you all a checkpoint, hopefully you include this in the picture. If not, here's the body. There's gravity, but it's also getting pushed upwards. Yeah, go for it. All right, so Angelina's going to take over.
All right. So the information given to us, let's write it out. We've got our mass is 2 kilograms. And there's an upward force. I'm just going to call this force A. And that's 25 newtons. What we're trying to get is acceleration. What is something that we can find already based on what we already have? Anyone shoot your hand up? Yeah. So we can say, all right, let's write out the equation that we normally use. And we can find our force of gravity using G. And I believe that's 19.6 newtons. So let's add that to our picture. All right. What should we do next before we can find acceleration? If we have some force pulling it up and some force pulling it down. Yeah. Yeah, so when we say combine the forces, what we're talking about is our net force. And so I like to use that up is positive. And so I'm going to do 25 minus 19.6. I think that's 5.4 newtons. Now we have a net force. And as was rightly said, we can set that equal to mass times acceleration. So I'm going to find my acceleration with 5.4, divide that by 2. That's 2 point something. What do we get? And how do I complete that answer? What's missing here? Yes, we want to make sure we put down units. All right, thoughts, questions, concerns?
Nice, thanks, Angelina. And thank you. So you're all going to see the LA and CA do this, and we might even get crazy. I may even have some of you all come up and do some solutions at some point as well. The reason for that is this is good, expressing, showing how to do a problem. That is a skill. Being able to convey to someone how you did something is a skill. That's why I asked you all, hey, how did you solve this? And things like that. So we want to practice that skill, and I want to give you all opportunities to practice it as well. Where'd the pen go? Oh, it's stuck. I didn't see it on there. So the cool thing about net force problems is they're actually very formulaic, meaning it's a very set process. And the process is draw a free body diagram, label all your forces, split them into X and Y, add up all your X's, add up all your Y's, and set them equal to MA. Every single net force problem basically is done in this manner. And so the trickiness just comes in identifying each force and all that kind of stuff. But it is nice and formulaic. All right, normal force. Another one. So, normal force is basically if something is touching a surface, this is how much the surface pushes it with. That's how I define it. If something is touching a surface, this is the force that the surface pushes it with. So right now, your all's butts are touching a surface, i.e. the chair. The chair is pushing up on you all. Ta-da, that's normal force. It is often equal to the force of gravity, but that is only if the acceleration is zero. If the acceleration is not zero, then they're not equal. One of them is winning. If the normal force is not equal to the gravitational force, one of them is winning. So if you all ever go in PSB, you'll see this. There's a physical sciences building is the building I'm in. If you all read the elevators, you'll see there's a scale in every single elevator with books on it. And it scales measure weight. When the elevator starts moving, the weight changes. Not because the books change their mass, but because the elevator literally is pushing upwards to move you. So the normal force increases to win. So yeah, some examples. If something is accelerating downwards, so if Fg is bigger than Fn, the acceleration will be negative. The other case is if Fn is bigger than Fg, the acceleration will be positive. Whatever one's bigger wins. If something is not speeding up or not slowing down, it's the same. All right, and I don't know if I have this question in here. Let's see. Yeah. So I'm going to wait a little bit for y'all to jot down whatever you want to jot down, and then I'm going to make a new question and see what y'all think. To test your understanding of this. Because there's no equation for normal force. There's not like Fn equal. So it equals Fg if the acceleration is zero. Otherwise, you actually have to do a bunch of the math to be able to figure it out. The other thing I want to point out, normal force, when you lean against a wall, the normal force is what's pushing you and causing you not to fall through the wall. Okay? So if I draw a person, there's me leaning on the wall. It's holding me up in trying times. The normal force isn't always upwards. When you lean on something and that thing pushes against you and keeps you from falling, we call that the normal force. Literally, if anything is touching a surface, that surface pushes against the person, that's called normal force. If you punch a wall, it's the normal force that hurts your hand. Okay? The wall pushes back. If you punch a wall, the wall will win. Well, okay. To be fair, if you punch a wall, you will push the wall with the same force that the wall pushes your hand. But your hand is squishier, and so parts of it will be compromised because they'll accelerate. The wall is not really going to accelerate because it's attached to a building with a lot of mass. You're not going to accelerate a building. But all the squishy bits in your hand will get accelerated. Anyway, all right, so let me make up this question. I'm going to actually make a few cycles of them. So, you are in an elevator. What is the sign of the acceleration right when the elevator starts moving upwards? Is it positive, negative, or zero? So you're in the elevator, you're on the ground floor, you hit the number 3. The second that elevator starts pushing you, what is the sign of the acceleration? Is your acceleration positive, negative, or zero right when it starts pushing you upwards? I have to let you respond. There you go. It is a clicker question. If it's ever multiple choice, it's a clicker question. It's good for your health. Now you'll know. All the elevators you rode, you never thought about it. Well, you know what? We're going to ask I'm gonna ask a whole bunch of these questions in a row, actually. What say you all? So we're considering as you start to move up, and that regime of the elevator is now starting to move. Why pause? Doesn't mean you're wrong. That's I always ask the question. Anytime someone gives me an answer, ask something. So when you're moving and acceleration. Oh, the answer will be true of the elevator and okay. And how fast are you moving when you get in the elevator? 0. And then the elevator starts going upwards. So what happens to the velocity? Velocity with the 0. The positive number. That denotes positive acceleration. We're assuming the elevator will move. Yeah, we're assuming the elevator works. Yeah, we're assuming we did not exceed the weight limit on the elevator. We are assuming the elevator does move. We are assuming you did not exceed the weight capacity of the elevator. It does start to move. It's not explicit, but I'll clarify that because it's a funny thing to say. There is weight limits on elevators for a reason. They can only move so much. All right, so I'm going to close this out in 5, 4, 3, 2, 1. All right, so to this end, this problem actually, you don't need to know anything about forces to answer this question. What's your initial velocity when you get in the elevator? When you start moving upwards, let's call that final velocity. Is it positive or negative if you're moving upwards? Positive. If your velocity goes from 0 to any positive number, you accelerate, your acceleration is positive. That's the only way you can go from a 0. That's the only way you can go from 0 to positive is it's going up. Your acceleration is positive. Now. Yep. Yeah, because your accelerate, your net, yeah. Just email me. I'll give you whatever. Your acceleration is positive because overall, your net acceleration is, and let's get into the next one. Let's get into the next one, which is going to be this. All right. Same exact problem. No, it's good. Anyone can always make mistakes. You're never so smart that you're above making mistakes. There's never a limit to I did 9 years of physics. You all have seen me make many mistakes in this class. That is not we are all equal in human beings. So just know that. And pro tip in life, if you ever make a mistake, just own it. Be like, yep, I made a mistake. Apologize if it's relevant. Well, you should, depending on what it is, apologize. Depending. It costs you very little to do so. And then, you just move forward in life. But don't be embarrassed about, yes, it's sometimes embarrassing, but you're in good company. It's not like the people you're talking to are perfect. So if you make a mistake, it's not like they've never made one. And keep that in mind both ways. Both ways. When someone else makes a mistake, give them some grace because you're no better than they are. All right. You're in an elevator. When the elevator starts moving upwards, so same problem. I'm just going to reword some things. When the elevator starts moving upwards, how does the normal force compare to the gravitational force? And the answers will kind of clarify what I'm asking for here. So how does the normal force, we're going to call that Fn. Oh, that's not what I wanted to do. So you all can think about this. Is it greater? Is it smaller? That's the question. I have to remember my macros. Or not macros, my hotkeys. F, G. All right, so yeah, the question is Fn greater than Fg? And then I get to copy and paste that. I don't have to deal with the subscripts. There's three options. Is it greater? Is it less than? Is it equal? Those are the only three options. Now we're taking, the first question was actually a kinematics problem. This one is now translating it to forces. Oh, and let me clarify, how does this for you? For you. How does the normal force on you? It's a small clarification. It probably won't matter for most people, but it matters the system you're talking about. The system you're working in matters. And my clarification there was my No, you're good. Yeah, exactly. Yeah, we drew a free body diagram, whichever was bigger. If you're not sure, draw a picture. Draw the vectors. Should one of them be bigger than the others? That's how you can think about this. Pictures help. All right, gonna give you all 5, 4, 3, 2, 1. Has your confidence been shaken? All right. So the answer is A. There we go. And I got to give the answer for the last one as well. All right. Now, the key to this, the really easy way to express this is draw your picture. Draw your free body diagram. We know there should be a gravitational force, but we know we're going to accelerate. We know our net force has to be upwards because we just said our accelerate. If A is positive, your net force is positive. If A is positive, then your net force is positive. F net equals ma. Mass is always positive. So if A is positive, then F net is positive. Meaning, my final force, if I draw my net force here in a nice little green arrow, it needs to be this way. So how do I make that happen? I need a bigger arrow. That's the only way you get a net force going up is if you have a bigger arrow pointed up. This is the thought process. This is the logic. All right. Now time to, well, I won't say anything. Same problem. I'm not going to give anything away. I want to see how y'all respond to this one. I have my guesses. You are in an elevator. What is the sign of the acceleration as it's moving? Not at the beginning, not at the end, in the middle. In the middle. In the middle. You know, I'll draw a beautiful picture for you all. You started on the ground floor. You're going up to the 10th floor, and you know you're like on floor 3, and you're just chugging your way on upwards. What is the acceleration as it's moving on? You are going up. This is after it's immediately started moving. It's before you've reached your destination. It's in the middle. It's in the middle of its journey. I'm purposely leaving out some words here because it gives away too much. There is some words I could use that would clarify things. I'm purposely leaving them out. Huh? Oh my goodness. Classic me. Thank you, thank you. Oh. And I'm an absolute Neanderthal. Well, the last one had a number. The last one had a number, so I felt bad enough to read it. What do y'all think? All right, give y'all a few words.
Just do Friday never trying to get it done until I don't worry about it. Yeah. Yeah, that's what I'm doing.
All right, closing out in 3, 2, 1. All right, there it is. Oh, so good. So good. Good job, everyone. Oh, I love it. It's rare to get 100%. 100% on anything. If you ever achieve 100% on anything, either the grading scale is very generous or you did like ridiculously well. Getting 100% on my test is really hard because being perfect is really hard. So anywho, it's always, across the sample of this many people, it's always great. So great job, everyone. Yes, it's a constant velocity. And then I'm just going to give you all let's do the same problem. So how does the normal force compare to Fg? And this is me just really, if you're in an elevator, as it's moving upwards, how does its normal force compare to Fg? Yes, none of the answers there. Boom. So taking that and then just translating it to forces. All right. And the whole point of this exercise is to help you all understand the relationship between Fn and Fg. Sometimes they're equal, sometimes they're not. And trying to understand when those scenarios are and actually, because a normal force is a concept more than an equation. Don't overthink it. Draw a free body diagram. You know A is 0. You know A is 0. You just answered that. Every single person got that right. Use that. I don't know anything about it. A lot of memorization. What's your yes, no, it's what's your age? I should have taken all my 4 reviews. Bill 9, yeah, modern day Bill 9. No, millennial Bill 9. Quotes from there. That's my favorite. Two of my favorites is, Millennial Bill 9 and Reddit post that saying goated with a sauce. So those are my top tier compliments I've ever received. Alright, we'll throw this out. Oh, you have a question? Alright, so we'll close this out in 3, 2, 1. So I am glad I asked this. I was wondering, I was like, oh, but it's the last one. There has been different answers here, which is great, because that means it was worthwhile for us to ask this. The answer is that they're equal. And really, here's the thought process. Here's how you approach all these problems. If the A is 0, so all the problems basically boil down to F net equals MA, and F net equals sum up your forces. This is a really fancy notation that just says, that's a summation sign. It just says add them all up. Add up all your forces. That's what that fancy little terminology there shows. So, what's my net force in this problem? If A is 0, if my total acceleration, this isn't gravity, this is my acceleration of the entire system. It's 0, so my net force is therefore 0. Therefore, if I draw FG, my net force, I can't even draw net force on here, it's 0. You can't draw a vector that's the size of 0. Fn has to be equal to it. Fn has, that's the only way they cancel. If I go 10 down, I have to go 10 up for those to cancel. So this is the thought process, y'all. This is what I have to get you all, these problems. This is your bread and butter. F net equals ma. F net equals add up all your forces in the x, add up all your forces in the y. Now, you will get an acceleration in the x, and you will get an acceleration in the y, so we'll do problems like that when we get there. But, yeah, it's good stuff. All right, moving onwards, how much do I want to do here? Okay, oh, look at that. When is Fn not equal to Fg when an elevator starts and stops? How funny is that, right? When you hit the bottom of a cliff, gravity stops winning. If you jump off something, gravity's making you fall. When you hit the floor, gravity is no longer, gravity is still pulling you down. Gravity doesn't turn off when you hit the floor, but now you have a force pushing up on you that's winning. The floor will win. Gravity will not win. Also, this is why, when you ride a roller coaster and you go over the top of one of those things and your stomach goes up, that's because your stomach is moved. It's Newton's first law. An object in motion remains in motion. An object at rest remains at rest. Your stomach fluids, when you go to the top of a roller coaster, keep moving upwards until they hit the top of your stomach, and then they come back down. And when you hit the bottom of the hill, the same thing. You've got a bunch of fluids in your body. When you go at the bottom of a hill, they are moving down. They keep moving down. If they're moving down, if you hit the bottom of the hill fast enough, they'll keep moving down. They'll leave your brain. That's when the G-forces make fighter pilots pass out. If they take a really sharp turn, all their fluids keep moving the same direction. They need time to kind of adjust. And you actually have to take this into account with rockets. Rockets, really interesting example. When a rocket goes up, there it is in all its rockety goodness. When it goes up, all the fluids in the fuel tank are going to get pushed to the bottom. So if your valve, you can't put the valve at the top because it won't get any fluids. Real world example of this is my friend in grad school. He raced cars legally in parking lots. It was legal. Well, yeah, at least this was. I don't know. This is at least legal. His engine ended up breaking. Pro tip: don't race the car that's your daily driver because you put a lot of strain on it. So when you take a sharp turn at the bottom of your car, you have an oil pan, and in your oil pan, the intake for it's in the middle. But when you take a sharp turn, all the oil goes to one side, not because there's any forces pushing on it, but because it keeps moving in the same direction. And therefore your intake doesn't get the oil anymore. And therefore your engine gets really hot. And then one of your piston rods actually slams through the side of your engine block and breaks it. Because it gets too hot and things get bendy when they get hot. So, his engine got totaled. But this is one of those things, when you're building devices, you have to account for how fluids, Newton's first law. It's not that they're getting pulled to the side, it's that they're not getting pulled when you make a turn until they hit something. All right, fantastic. All right, going to skip that. We're going to move onwards. For the sake of the lab today, I'm going to actually jump around. We'll do some of these problems next week. It may look like we have a lot of things left, but we have a lot of time next week, so we'll be fine. Tension force, I'll mention this very briefly. It's really simple. Tension force is literally if you have a thread, a cable. Let's just do an easy example. Something hanging from a ceiling by a string. Gravity pulls it down. Tension force holds it up. So tension is what we call it when you have a string or some rope or some cable that's pulling something. We call it tension because the rope's in tension, and that's just the terminology we use. So we call that a force. We often do just label it as T, but if you want to keep things kind of consistent, you could do like FT, force of tension. You will see it labeled as capital T. You'll see it labeled as maybe FT. Mileage may vary. There's lots of different ways to write things. So there is no equation for tension force. Like normal force, you kind of just have to calculate it, or it has to be given to you. So a classic problem is the one I just gave. Something's hanging from a ceiling. Calculate the force due to tension. It will equal the force due to gravity. That's a classic. That's the simplest case. And it's literally the next problem I'm going to give you. Because it is the simplest case. And then I'll show you how it can get more complicated. If you had so much fun in one dimension, why not two? All right. Boom. A 20 kilogram chandelier hangs from the ceiling. What is the tension of the wire holding it up? Draw a picture. Calculate this really quickly. We won't do the more complicated example today, because I got to quickly show you all spring force, and then we'll start talking about the lab. $20 kilogram chandelier hangs from the ceiling. What's the tension? Draw a free body diagram. Draw a picture, y'all. And if y'all ever want, if you haven't noticed this actually shows you student responses. So you can, yeah. So that I use that to kind of determine how long I need to spend on something, and also if a lot more people need help.
Is this number of responses?
Yeah, that's total A, B, C, D, E.
Oh, wow. Okay.
It's just handy. So it's a way for me to see the responses without
That's awesome.
Yeah, it's very handy.
Yeah.
It's very handy to give me a sense of how people are doing in progress. I can technically hit that little results thing, but then everyone sees it, and then they start
Second guessing themselves.
Yeah, or changing their answer. How'd you do? What'd you get? No comment. Not weight. Yeah, weight now means force due to gravity. So subtle. Yeah, weight's one of so kilograms one of the
This shows you the total responses. This is A, B, C, D of people live doing it.
Cool.
Yeah, so this is where you have to be really careful. So this is where we have to be careful with our terminology. So 20 kilograms here is mass. But it also can be the 20 kilograms, yeah. So is so I had to say 196 grams is equal. So 196 newtons equals because here we're not going to mass as weight. So it's not 20 kilograms. They're used differently. Yes, it's newtons to pound, not kilograms. But so 1 kilogram of weight, 1 kilogram will and there's a history to it that I looked up at some point. So, there is a good reason. All right, I'll give you all 5 more seconds. We're looking pretty good on this. We'll close this out in 3, 2, 1. We were so close. All right, so drawing a quick picture of this. Boom, there it is. It's hanging from the ceiling. Look at that chandelier. So yeah, you got the force due to gravity. You have the tension force. How do they compare to each other? They're the same. How do we know they're the same? In this there's no acceleration. I didn't tell you in this problem that the chandelier is not accelerating, but hopefully that's not like nothing in this room that's hanging from the ceiling is swinging left and right, or falling to the floor, or flying towards the ceiling. That's something you have to like take your obvious stuff. Obviously, it's not moving, and you have to translate that to the acceleration is 0. I will not tell you that. If something's hanging from something, you have to know that means the acceleration is 0. It may sound obvious, but it is a skill. So therefore, the net force is 0. Therefore, tension equals Fg. Therefore, mg. You do the math. You get the answer. Ka-chow. We were so close to perfect. We had like 1 or 2 people here and there. That's okay. I'm not offended. Doesn't bother me. All right. I am not going to do this next problem today, but I will do it next time. Feel free to try it in advance. So here's the recipe, y'all. This is how you do these problems. I've already said it in words. Now it's in writing. Draw a free body diagram. F net equals MA. X and Y are independent of each other. So you are not just doing F net equals MA. You are doing F net X equals MAX. You are doing F net Y equals MAY. And then you add up all the forces. I should have put that here. Actually, I can just do that now through the power of typing. F net equals sum of forces. So in the same logic, so F net X equals the sum of all forces in the X. F net Y equals the sum of all the forces in the Y. This little sign here, if you haven't, hopefully you've seen it, you'll definitely see it in Calc 2. Series expansion. Sum. It's capital sigma. Here's your daily Greek lesson. That is capital sigma. So anywho, it's an important symbol. I don't want to write the word sum a bunch of times. The reason we use symbols is because one thing is quicker than writing three things. Sum is more letters than a sigma sign. Anyway, all right, this last one is going to be killer. If multiple objects move together, you should consider them together. I'm going to go ahead and give you a foreshadowing of this last one. I'll show it for like 2 seconds. It's this problem. It's the classic mass pulley problem. We'll see it eventually. We'll get to it eventually. Not today. All right. This problem as well, we're not going to get to today. We had so much fun finding the tension in one dimension. Why not in three? Or not three, two. But there's three tensions. It's kind of hard to see here, so I'm going to zoom in. There's three tensions here. So you draw a free body diagram here, and you have a tension 3 going up. And then you have the pleasure of drawing another 3 body diagram. These are all the tensions. So I'm not going to solve this right now. Feel free to try it on your own, but I'll do it next on Tuesday. For now, let's go ahead. I'm going to jump to the lab and start spending a couple minutes, then I'll give you all a break. All right, actually, we're going to do this a little differently. We're going to talk about the lab, and we're going to come up with a plan, and then I'm going to give you a choice of kind of whether or not you want to just start working on it and get it done, or whether you want to take a break. I mean, thought process there is probably many of you probably just would like to get out of class earlier rather than have a 5-minute break. But if you want to have a break, you can. So anywho, but I need to talk about the lab before I give you that autonomy and decision-making process. So, real quick, I'm just going to jump down to the spring force. All I need you to know is the equation for it. Where are you at? Spring. Okay, force due to a spring is really simple. It's Kx. You're going to need this for today's lab. We will come and visit this slide in the future, so don't worry. But I'm just going to briefly say the force due to a spring is Kx. K is called the spring constant. It's how stiff your spring is. The bigger K is, the more stiff your spring is. That's kind of the best way I can generally say that. It's called the spring constant. And X is the distance from equilibrium. So, a spring exists in a certain state. X is how far you stretch it or squish it from that state. How far you stretch it or squish it. So if you stretch it 1 meter, that's X. And equilibrium is if you let it go, nothing is pushing or pulling it, nothing. Then that's its kind of equilibrium state. And you can measure that distance and all that jazz. So, anyway, I need to mention this for the lab today. All right, so now that I mentioned this, we're going to jump to the lab and we'll spend some time as a class deliberating a plan. It's one of our questions. The reason we're doing it as a class is ultimately I need to make sure that everyone has a plan that works. One of the worst things that can happen is if I tell you all, come up with a methodology, and then half the class comes up with a bad methodology and realizes it at the end, and it's very sad for them. So we do the checks in the beginning. We do it as a class kind of thing. I'll give you all chances to work on it and think about it, but as a collective. So go ahead. Jump over the modules tab is where you'll find Lab 3. I published it on, I think I actually made it on Tuesday. Sooner than usual. Good job, me. Fun fact, last week we learned that me making new lab groups each week results in mass confusion. So I deleted all the old lab groups, and every single week they'll kind of get deleted and refreshed. So you are going to make your own lab. Each week you will join a lab group again. Each week that will happen. It makes the grading much smoother. It helps us adjust for absences. It requires a little bit of time on your end for a lot of benefit on yours and our end. So join a group. They're all fresh. You don't need to scroll to the bottom. And every week I'll kind of delete all the old groups. Every week we start fresh with that. So you can go ahead and do that now. Groups are reset. You don't need to do a bunch of scroll, but you do need to join a group. If you do not join a group, yep, there we go. This is to make Angelina happy and therefore you happy. It's like the SAT. If you don't bubble in your stuff correctly, there may be delays in your grading. If you do not join a group correctly, there may be delays in your grading. Any group that... Remember, the max group number is 3. So as long as 2 or any group that's got 2 people is a good one to join, or 1 person. You cannot be in a group with more than 3 people. You cannot be in a group with 1 person. That is not a group. You cannot be a wolf pack of 1.
So this is lab 3, but on this is lab 4.
Gosh, did it say lab 3? Oh. No, it says lab 4. Oh, but it says lab 3 on the other thing. Yeah, that's weird wording, isn't it? It's the lab we're doing. We did lab 0. I don't know why I chose to call it. I called it lab 0 because it wasn't graded. This is technically our 4th lab. So now my numbering is all confusing.
There was one that worked.
All right. So there's a bunch of words here, which you're welcome to read. It may actually help you come up with the methodology because it's kind of hidden in here. But look, there's the force of a spring, Kx. In case you missed it from before, it's there. There's other things here, woo. There's other things here, woo. But here's what I want y'all to brainstorm. Do not proceed on this until I kind of, as a class, said, here's the procedure we're going to follow. Do not start grabbing things because the result is I don't want anyone to think they have a good methodology and realize only at the very end that their methodology was crap. I do not want that to happen. You don't want that to happen. So this first part, we're going to, there's kind of a checkpoint as a class. So my questions, there's 2 questions here. We're going to do one at a time. Design an experiment given a spring, some masses, and a ruler. That's all you got. A spring, some masses, and a ruler. Design an experiment that will let you measure the spring constant of an unknown spring using a known mass. Come up with some methodology. And whatever methodology you come up with does need to be listed in here. This is also good practice. Whatever you come up with, so jot this down in experimental design. The description should be detailed enough that someone else can repeat your experiment. If they can't repeat it, then it's like giving a recipe to someone and they can't follow it. So spend some time. I'll go around. We'll chat with you, see what y'all come up with. If you figure out this one, try the next one.
Did you get this?
Okay, also join your groups on the website because it doesn't work on the app. So if you can't see the people tab, if you go to people, you don't see anything, just go on the website and it'll work there.
No, it doesn't have to do that. Don't break my springs. Don't break my springs. One of the rules of this is don't overstretch them. Oh my God. My hint to you all, you're going to hang a mass from it, draw a free body diagram of what the forces will look like when the mass is at the bottom. Oh yeah, they have to know the mass. And they don't know the mass?
Yeah.
When it's just hanging there.
So
how is that used?
Oh yeah.
What force would be, so gravitational force, spring force would be gravitational All right. It's unfortunately a little tricky for me to draw on this, so I'm going to make a new slide and draw a picture here. So you got your spring with nothing on it. And then you have your spring with it hanging from it. How much it gets stretched, that's going to be X. You all tell me, when it's hanging from the bottom, what forces are acting on it? Gravity. Which way is gravity? Down. What else is acting on it? The spring force, which is which way? Up. We'll call that Fs. S for spring. All right. Question to y'all. What's the acceleration what's the net force when it's hanging at the bottom? 0. So F net equals 0. And if I add up my forces, you get Fs plus negative Fg. And what's that going to equal? So how does the spring force compare to the force of gravity? They are equal to each other. Why is this useful? Let's just put the variables in. Do you know the mass? Yep. Do y'all know G? Do you know X? You can calculate K. So this is the process, y'all. This is the process for this. It's hanging a chandelier from a ceiling. But instead of tension force, it's spring force. And this is how you can calculate the spring constant of any spring. You can do this at home with any spring you may have. How exciting. It sounds silly, but it works. All right, so that is step one. That is step one. That's how you're going to do that. Now, it does say, make sure this experiment includes multiple trials. That is good. Use different, like, math. Get a few different masses. Try it out. It'll work the same. Just do a few measurements. This next one, I'm just going to tell you all kind of what to do for the sake of time. I haven't told you all oscillations. So the second one is just kind of an interesting one. We, unfortunately, probably won't talk about harmonic motion in this class. But the time for one oscillation is called the period. And there's two ways you all could do this. How could we measure the time it takes for that thing to make one oscillation? What equipment do you all have on you that would let you get a really accurate time of this? A camera. You all could record a video and do that. That is an option. For the sake of time, I'm not going to have you do that because that takes longer. Because if you wanted to do that really well, you'd have to import it into Logger Pro, or not Logger Tracker like we did last week, and then track it and do all those kind of things. So we're going to do something different. We're going to do the easier option. It's what we did the first week, which gave us bad data, but we're going to make a correction to it to get good data. What's another way? What's the other, like, crappier but still valid? You could just use a timer. But here's the problem. What did we run into when you all used a timer when it went down the inclined plane? How was your data? Horrible! What's the major problem with using a timer? Human, like the reaction time is, even more specific, which is great. Now, to avoid that, what I ask for you all to do, so I'm just going to tell you all what you're going to do here. You are not going to record the time for one oscillation. You're going to use a timer. You're going to time it. Record 10 oscillations. If I record the time for 10 oscillations, how can I get the time for one oscillation? Divide it by 10. And I'm not going to tell you why this is better, because I want you to tell me why it's better. How does measuring time across 10 oscillations reduce the error? So that's a question for y'all to answer in the future. So anyway, this are your two experiments. Hang a block, and then it has you make graphs and stuff like that. And the other one, just have the thing wiggling. Someone record that time, and you only have to do that like 5 times. So it shouldn't take too long. Pro tip, you have multiple people in your groups. Divide the labor. While someone's making the graph of the first thing, someone else could be oscillating it and timing it. The beauty of group work is it's a group. You can split up the work. So do so if you want to. All right. You do you. You got an hour, 20 minutes until we officially have to get out of here. Same as always, check with a group. Check with one of us before you're done. Nope. There's a bunch of springs here, so you're going to... How many other boxes are there?
There's tons.
Oh, great. Grab one spring. You don't need multiple springs. Only take one. Different colors mean different things. I'm not going to tell you what they mean. Doesn't matter.
Yeah.
And then where's the masses? The masses are...
Yeah, exactly.
All right, springs are there. Masses are over here.
Oh, dude, that was the one I was gonna grab.
Don't break my springs. Don't overstretch them. If you overstretch a spring, you undergo. You'll learn about this thing. There's plastic deformation and there's elastic deformation. Plastic deformation when you've exceeded a certain thing, you don't grow. And it doesn't go back. If anyone's played with a slinky, you probably broke it because you stretched it too far.
Wait, the red one was fire.
I will put these here.
So there's a lot of mass there. You don't have to hang it from all that mass. You know, lay it from 1, then 2, then 3, then 4, then 5. Like, you got this. Thank you.
Where'd you get the ruler?
One more thing that you have to set up. It's actually just anchored to. It'll work. As long as you measure this. You're not measuring the oscillation.
I want to get the smallest.
Alright. I leave it up to you how to hang the screen, but if you want, there's some clamps here. There is some clamps over in this box down here that can clamp to the side of your table, and then they have a little screw you can unscrew and kind of put your thing through it, and that's an option. But this is up to you all. That's however you want to hang it. You can hold it from your finger if you want to.
Plunger part.
So that first one is the whole hanging. Yeah, so I wouldn't go